Let's look at galvanometer. A galvanometer is an electrical instrument used to detect the passage of current. Its working depends upon the fact when a conductor is placed in a magnetic field, it experiences the force as soon as the current passes through it. Due to this force, a torque T acts upon the conductor if it's in the form of coil or loop. T is equal to NIBA cos alpha, where N is the number of turns in the coil, A is the area, I is current passing through it, and B is the magnetic field in which the coil is placed, such that its plane makes an angle alpha with the direction of B. Due to the action of torque, the coil rotates and thus it detects current. The construction of moving coil galvanometer is shown in figure 14.16a. A rectangular coil C is suspended between the concave shaped poles N and S of a U-shaped magnet with the help of a fine metallic suspension wire. The rectangular coil is made of enamel copper wire. It is wound on a frame of non-magnetic material. The suspension wire F is also used as one current lead to the coil. The other terminal of the coil is connected to a loosely wound spiral E, which serves as the second current lead. A soft iron cylinder D is placed in the inside of the coil to make the field radial and stronger near the coil as shown in figure 14.16b. When a current is placed through the coil, it is acted upon by a couple which tends to rotate the coil. This couple is known as deflecting couple and given by NIB cos alpha, A cos alpha, as the coil is placed in a radial magnetic field in which the plane of the coil is always parallel to the field, figure 14.16b, so alpha is always 0. This makes cos alpha 1 and thus deflecting couple is equal to NIBA. As the coil turns under the action of deflecting couple, the suspension wire figure 14.16a is twisted, which gives rise to a torsional couple. It tends to untwist the suspension and restore the coil to its original position. This couple is known as restoring couple. The restoring couple of the suspension wire is proportional to the angle of deflection theta as long as the suspension wire obeys Hooke's law. Thus, restoring force C theta, where the constancy of the suspension wire is known as the torsional couple and is defined as a couple for unit twist. Under the effect of these two couples, coil comes to rest when deflecting torque is equal to restoring torque. NIBA is equal to C theta, I is equal to C upon BAN theta. Thus I is directly proportional to theta, since C upon BAN is equal to constant, thus the current passing through the coil is directly proportional to the angle of deflection. There are two methods used for observing the angle of deflection of coil. In sensitive galvanometers, the angle of deflection is observed by the means of small mirror attached to the coil along with a lamp and scale arrangement. A beam of light from the lamp is directed towards the mirror of the galvanometer, and after the reflection from the mirror, it produces a spot on the translucent scale placed at a distance of 1 meter from the galvanometer. When the coil rotates, the mirror attached to the coil also rotates and the spot of the light moves along the scale. The displacement of the spot of the light on the scale is proportional to the angle of deflection, provided the angle of deflection is small. The galvanometer used in school and college laboratories is a pivoted type galvanometer. In this type of galvanometer, the coil is pivoted between two jeweled pairings. The restoring torque is provided by two hairsprings which also serve as current leads. A light aluminum pointer is attached to the coil which moves over a scale. It gives the angle of deflection of the coil. It is obvious from equation 14.17 that a galvanometer can be more sensitive to give large reflection for a given current. If C upon BAN is made small, thus to increase sensitivity of a galvanometer, C may be decreased or BA and N may be increased. The couple C for unit twist of the suspension wire can be decreased by increasing its length and by decreasing its diameter. This process, however, cannot be taken too far as the suspension must be strong enough to support the coil. Another method to increase the sensitivity of galvanometer is to increase N, the number of turns of coil. In case of suspended coil type galvanometer, the number of turns cannot be increased beyond a limit because it will make the coil heavy. To compensate for the loss of sensitivity in case fewer turns are used in the coil, we increase the value of magnetic field employed. We define current sensitivity of a galvanometer as the current in microamperes required to produce 1 mm deflection on a scale placed 1 meter away from the mirror of the galvanometer. When the current passing through the galvanometer is discontinued, the coil will not come to rest as soon as the current flowing through the coil is stopped. and it keeps on oscillating about its mean position before coming to rest. And in the same way, the current is established suddenly in a galvanometer. The coil will shoot beyond its final equilibrium position and will oscillate several times before coming to rest at its equilibrium position. As it is annoying and time consuming to wait for the coil to come to rest, artificial ways are employed to make the coil to rest quickly. Such galvanometer in which the coil comes to rest quickly after the current passed through it or the current is stopped from the flowing through it is called stable or dead beat galvanometer.